Well, so we have seen lots of closure properties, and what do they have? So you start with some language, and using some operations you produce some other language. For example, you take union or intersection or complement or reversal or quotient. So you do some operation on some language to start with, and then you come up with some other language, and then show that if the initial language is regular, then the language that you produce, that is also regular. Uh, so here we have another operation, it's called substitution, and later we will see a special case of this thing called homomorphism. And then these are maps. So if you have a homomorphism, you have inverse homomorphism, and this homomorphism, it looks a lot similar to the homomorphism you see in group theory or over rings or something like that. So you have this substitution, a special case called homomorphism, and the inverse of that, inverse homomorphism. And for all these operations, we will show that regular languages are closed under these operations. So let's start with substitution. Now, substitution is a map from, say, so you have two alphabets, okay. So it maps string from, say, this alphabet. So sigma star means you are talking about strings over sigma. So it maps strings of over this sigma to some language over delta. See, the mapping is from a string to a language. So here you have the set of all strings. Here you have the set of all languages over delta. Okay, so the map is like this. You provide some string over sigma, and this produces some language over delta, right? It's not a specific string over delta. This f of w is an entire language over this delta. Okay, please notice that thing. So and so you can put any string here, you get a corresponding language. So if you put a symbol here, so a symbol is also a string of length 1. So if you put a symbol a here, so this fa, so fa is then again a language over this delta, but this language is a regular language over delta. Okay, this is one property that this map satisfies, that f of a is regular language of over this delta for any symbol a, right? And then it also satisfies this property, that if you have some string x and if you have some symbol this, so it kind of breaks this into these two parts. So this is just so if you take concatenation of this string and then take f, so this is a concatenation of these two. Now see, this is a language, okay, this is also a language. So this is concatenation of two languages. Here we are talking about concatenation of two languages. Okay. So now this equation looks a lot like the homomorphism, right? So in homomorphism, I mean in group theory or ring or whatever, what was the equation? H of x y is equal to h of x into h of y. So this is where the similarity comes. Now if this is the case, so first of all you see that you can break this x also into a symbol and a shorter string. So you can break this entirely into this f of symbols, right? So what happens is, if you take f of a1 up to an, where this ai's are symbols, so this ai's are coming from sigma. So if you take f of this, so then it's actually f of a1, f of a2, f of a3, f of a4, and what are those? Those are regular languages over this delta. So this is what you have according to this definition. So this is f of some string, right? Then we define f of a language over sigma. Okay. So here we are providing a string and we are getting a language over this delta. But here we are providing a language. Okay, we extend the meaning of f. And what does this mean? So this is the union of all these fw's, where this w is in L. So you take all strings in L, you take all the fw's, right, for all these strings, and you take their union. So this big union is what this f of L is. Okay. So this is the definition. So just if you need time, you just pause the video and just soak in this definitions. Okay. Well, so if you are okay with the definitions, let's see some examples. Say here we take sigma to be 0, 1. Okay. And we take delta to be AB, right? So f of 0 and f of 1, that is what defines the substitution, right? So once you define this f for each symbol, then this f is defined for all the strings, and once it is defined for all the strings, it is defined for this L also. So you just need to define it for this symbol 0 and 1. And this is how it is defined. So this f of 0 is A and f of 1 is B star. And you see that these are boldface. So these are regular expressions. Okay. So what does this boldface A mean? So this means the singleton set A. Right. This means the singleton set A. Right. So what does this mean? This means you take the singleton set and then take its clean closure, right? So these are regular expressions. So if you define this substitution, then yeah, you see that this thing is a language over this. This f1 is also language consisting all strings of B. And then what is this thing? So yeah, you go there. So it is concatenation of this language f0, f1 and f0. So it is this one. So this is a language. Okay. This is a string. It's mapping the string to this language over AB, right? And then you can take some language over the sigma. Suppose you take this language. Again, these are all regular expression. So you should be comfortable with regular expression to read this sort of thing. So please, if you are not comfortable, go back to those regular expressions video. And okay, so this is a language over this sigma. And if we map this, what do we get? We take all the strings here, all the string W in this L, and then take the union of all these FWs. Okay. And if you do that, you get this thing. And it is not hard to see what is happening from here to here. See, this means what? So this means you have some number of zeros, say 0 to the I, then you have either a 0 or a 1. So then you have either a 0, or maybe you have 0 to the I, then a 1, and then some number of 1s. So 1 to the j maybe. So again 1 to the j maybe. So this sort of strings are in this language. Now you are replacing 0 with A, right, and you are replacing 1 with B star, right. So if you do that, you see that it's just replacing these regular expressions, this 0 and 1, by the corresponding regular expressions here and here, right. So each symbol here is being replaced by some language. This language is given by these regular expressions. So here you have a regular expression for this L over sigma, this L over sigma, and now in this regular expression you take the symbols and replace them by the corresponding regular expressions over delta, and then you get this thing. So this 0 is replaced by A star. So in fact this is this 0 is replaced by A and 1 is replaced by B star. So this is B star, B star. So now if you simplify this thing, you get A star, B star, but that you can prove actually. So now how to prove this? You remember some identities we talked about when we discussed regular expressions. So so B star star is just B star. Okay. So you have A star, A plus B star, sorry, A plus B and B star. So if you do this multiplication, you get A plus B star and A star B plus, and this together can be captured in A star B star. So yeah, so this simplification has nothing to do with the substitution anyway. You should be comfortable with this sort of simplification. But the point is, the crucial point is, if this L over sigma is given as a regular expression, where you see the symbols for this over this sigma, and you are given this f0 and f1s as regular expressions over delta, so you just replace these zeros and ones by these regular expressions and you get this. Now this is I mean, this is the common sense feeling that this will work, right? Now the rest of the thing is to formally prove that this will actually work. Now you see that this substitution map, this F, has certain properties. So it follows from the definition. So first of all, you see that f of epsilon, this empty string, is the singleton set containing epsilon. Why? Because here if you put x equal to epsilon, you get f of a is f of epsilon concatenated with f of a. So these are languages, right? So this is a language and this is a language. And when does this equality hold? This holds if and only if this language is just this language. Okay. With respect to concatenation of languages, this language acts as identity. And if you map a empty set, you get an empty set, so phi maps to phi. That's most trivial. And then it has this property that if you take f of L union L2 or L1 L2 or L star, you can push this f inside. So this becomes f of L1 union f of L2. This becomes f of L1 in concatenated with f of L2, and this becomes f of L clean star. Okay, so these are pretty straightforward to prove from just this definition, and obviously the definition of, say, concatenation and clean star. So I have just written this proof here. I mean, there is nothing to explain as such. You just follow these steps. For example, this is by definition, right? What is L1 L2? By definition, L1 L2 is this expression, right? And then when you are taking f, by this definition you are taking union over all this f of this strings. So the strings that is in this set. So now if you do this, then this follows from this property, right? So it's not about just one string and one symbol. So this implies that f of xy is actually, so it implies that f of xy is f of x, f of y, right? So it follows from that. And then these are languages, right? Again, this is a language, this is a language. So concatenation of these two languages, how do you do that? So you take okay, so first of all we rewrite this as this expression, right? Because you are taking union over this set. Okay, so that means you are taking all the elements of this set, and these sets are also coming from this choices of x coming from L1 and y coming from L2. So you take this thing and then yeah, so what is the definition of concatenation of these two languages? Like so this w should be x prime y prime, such that this x prime is coming from this and y prime is coming from this. And then we separate this out into these two parts. So we separate this x. So you see that this x is coming from L1 and x prime is coming from this f of x, right? So that means we can separate this out here and separate this thing out here. So this is the concatenation of these two languages, right? Again, the concatenation is x prime y prime, where this x prime and y prime are coming from this thing. So concatenation of these two languages. And again, what is this thing? So this thing, if you see that it's actually this thing, right? And you have again this and this. Okay. So I'm not explaining this childish thing. You just pause the video and see that this is this. And by definition, this is f of L1, this is f of L2. So perhaps this was the most lengthy, and once you have this, this is even simpler. So again, I'm not explaining this, it just follows from the definition. So here we have this L1 union L2, and by this definition you take this big union, and you can break this big union over this small union here, and then this is f of L1, this is f of L2. Here maybe I should just mention one thing, that this is the union of all the Li's, right? And we have already proved this for union. So this is just one union, you can take I union. So this is yeah, so it's not I union, it's infinitely many union, but anyway, you can take this union, and then you can push this inside, and once this is inside, so you can take this property. So you can take L1 to be L2, and you can take multiple concatenation. So this tells you that f of Li is f of L to the I. So f of Li goes here, so that becomes f of L to the I, and if you take union, and you get this thing. Okay, so these are pretty straightforward to prove, but anyway, so most importantly, then we have all this property that f of epsilon goes to this epsilon, f of phi goes to this phi, and F kind of, you can push this inside this union, concatenation, or clean star. So once you have this, now as I said, so this L need not be, this L1 L2 need not be regular here for this property to be satisfied. In fact, we are not even using this part, that this f of a is regular. So here you do not need anything to be regular. From the definition of substitution, this happens for all languages, regular or not. So now we are taking regular languages here, and we are expressing that as regular expressions, right? So we already proved this part. So this is same as the previous slide. We have all these properties. So now if we write it in terms of regular expressions, and if we assume that now that this L1, L2 are regular languages, so then what we have, so this phi in regular expression is this boldface phi, right? So this means empty set. So this set containing empty string, so that is expressed as this boldface phi as a regular expression, right? So and this f of a, so this is some regular language RA, and say that this RA is denoted by this regular expression small r. So small r denotes this regular language capital R. So this is a regular expression. Okay, this is regular expression, this is the language. So that means f of a is this one. So we can rewrite this thing in terms of regular expressions, and then this is also easy to write in terms of regular expression, provided we take this L1 L2 to be regular. So the difference is here we do not need this L1 L2 to be regular, but if we restrict ourselves to regular languages, so then we can take say R and S such that this L1 is just say the language denoted by R, and L2 is language denoted by S. So then union is written as plus, so this union becomes this plus this. Okay, so we can translate these properties into this equations over regular languages, provided we are only talking about regular languages. So this f, we said that this is so we started here that this is a string, and then we get a language here, and then here we extended the meaning where we provided a language over sigma, and we get a language over delta. So now we are so here instead of our language we are providing a regular expression. So that is the same thing. The language denotes, the regular expression denotes some language, right? And then you get back a language, but then again this language is we are getting as a regular expression over delta, right? So these languages are now expressed as regular expression. So that means we are talking about regular languages here. Okay. Now what we can prove is that so since we have this map, so this completely defines this for all regular expression, you see, because how do you construct the regular expression? You have this thing for phi, epsilon, and all the symbols, and then you combine this using this plus, concatenation, or star, or whatever you get, you can again combine that using plus, concatenation, star to get arbitrarily complex regular expression, right? So this defines this f for all regular expressions. So now we prove that if t denotes say a language L, then this f of t, so again this t is a regular expression, and you get back another regular expression. So this f of t is the regular expression which denotes this language f of L. Okay. So once we have that, we see that this f of L must be regular because it is expressed by some regular language, right? So if it is expressed by some regular language, this must be regular. So this as a corollary tells you that if L is regular, then f of L is regular. Now how do you prove that? We have already proved all the things. So just to formally say this, we take this T and we do a induction on the number of operators in T. Okay, number of operators in T means the operators are either this plus or concatenation or this clean star. So this T will contain some number of this operators. So we do a induction on that number of operators in T. So we have done similar things while proving something in regular expression. So you have already seen this thing there, induction on this parameter. So the base case is there are no operators, zero operators. So what are those expressions? Those are precisely these expressions. Is either this phi or epsilon or this a for some symbol, right, in sigma. So you see that T is a regular expression over sigma, and this f of T that you get, that is a regular expression over delta, right? So here we are taking regular expression over sigma. So these are all the possible regular expressions which has no concatenation. And then the induction step is what? You take some T which has many operators, but then this T can be broken down into either this form. It is either concatenation of two things, or it is union of two things, or it is clean star of something else, right? So this T must be either this or this or this. So that means if you consider this R or S, they contain less number of operators than T, right? Because you are kind of taking out this concatenation operator, so, or this plus operator or this star operator. So this R itself or S itself contains less operators than T. So then by induction hypothesis, we have this thing, right? So the language that is denoted by R, if you take the substitution over that, so that is the language which is denoted by FR. So this is what it means. The language, so this L is what? This L is L of T, right? And this the language which is expressed by f of t is what? L of f of t. So you are claiming that this is actually this f of L. So this thing. So you are claiming that this is f of L of t. So this is what this statement means mathematically. So this is so by induction hypothesis we have this over say R and S because they have less number of operators. So once you have this, then you see that if you take L of this thing, so we have already proved this thing because of this and this, right? So okay. Because say if you want a further breakup, what is this? This is L of by this thing f of R and f of S, right? So this means there is this property, so this will be L of FR union L of f of S, and yeah, so this proves that regular languages are closed under substitution, and not only that, it gives you a method to construct okay, so here it is shown, so this step follows. Okay, I have the proof here. So from here you can have this from here, and from here to here you go by the definition of regular language, right? Because in regular language this plus means union. So this is by the definition of regular language. So once you have this, then by induction hypothesis you have this thing. So L of f of r you replace by f of L r, and similarly here, right? And then this to this we use this property. Okay, from here to here, and then again by the definition of regular languages. So yeah, so this is just class of this and this, right? And then you have f here. So the switch of L and so the order in which L and F are applied, so that switch happens in this step, right? So here is the step where you go from a regular expression over sigma to a regular expression over delta, because yeah. Okay, so similarly you can have the proofs for this concatenation and clean star. I'm not writing those, so you can work that out yourself. Now homomorphism, as I said before, it's a special case of substitution. So what is the special case? So in substitution, this f of a, so f of a was some regular language LA, right? So there is a set. So for homomorphism, this set is singleton, right? So this just contains some string, say WA, say. So instead of seeing this as a mapping from a symbol to a set, since this set is singleton, we can just map it like to strings over delta. Okay. And again, so this is for a single symbol, and as we have seen in the substitution, so by this property, so by this property it follows that if you have multiple symbols, then each of that thing is you take each for individual symbols and you concatenate that, right? So now you just note that we have slightly changed this domain, so the range, so that you are providing a string over sigma and you are getting back a string over delta, not a language anymore, because as a language it is just a singleton thing. So you better just focus on that single string itself. So that's the only difference. Okay. And since this is a special case of substitution, so it immediately follows there is nothing to prove anymore for this homomorphism, that regular languages are closed under homomorphism. So what does that mean? That if L is regular, then H of L is regular. And H of L as before, so we define, so we have defined this for strings, right, from string to string. So H of L we can define just like before. So h of w, where this w is coming from L. So this will be the same definition as that for this. Okay, so here we have union, but here you see that these are now just singleton sets here. So if you just have this a singleton set, instead of taking a big union outside, you take just all those elements. So this is the definition of HL. And by the previous thing, you also have this closure. Now, since this is a map from the strings here to the strings there, you can consider the inverse map. So just the mathematical, what you know from regular mathematics, the inverse of a map. So how do you define that thing? Okay, so before I discuss the inverse, here is an example. So the same example, now we have all these things. So this f of t that I was talking about, this f of t is defined using these rules, and these actually follow from these properties. So this, what is this? This is actually this substituting the symbols in one regular expression with the regular expressions as specified by f. So in this when we encountered this thing, we mentioned this, like this f of 0 is a and f of 1 is b star, and we said that you replace just this 0 and 1 with this a and b star, and that will give. So now just to see that this f of t is actually doing just that. So if you see this example, so you are doing f of this thing, so this whole thing is your t, right? Now from here if you have a concatenation, you can break that up. You can push the f inside. If you have a plus, you can push the f inside. If you have a star, you can push the f inside. So from here first you break the concatenations, so you get f of 0 star, f of 0 plus 1, f of 1 star. So these are still regular expressions over sigma, and then you can take this clean star outside, right? You can push this f inside this thing, this plus. So this is what you get. So what is happening is that you are replacing this 0 with f of 0, you are replacing 1 with f of 1. Now in a regular expression you can have also phi and sigma, right? So you will also replace that with f of phi and f of sigma, but that is just sigma and phi. So yeah, so f of sigma is sigma, f of phi is phi. So if you have some sigma or phi in your regular expression that you start with, you keep that as it is. The other symbols you replace by whatever is given. So f of 0 can be some regular expression, this can be some regular expression, this can be any regular expression. So you just replace this 0 and 1s by that, and you get this. So this is what it is. Okay. So now, as I said, I now have this homomorphism and this homomorphism is a map from string to string, and now consider the inverse map here, right? So it's just the same definition that you have for inverse of any map in mathematics. So it's so now this, say, H map, so this can be a many to one map, right? So you have this sigma star, and this is mapping this to delta star. So this can be a many to one map. So you can have multiple strings here which maps to the same string. Okay. So if you take inverse of say just this W here, you can get multiple answers here. If you take inverse of something which is not image of anything here, so then you get phi, right? So for example, take this sigma. So sigma is 0, 1, 2 and delta is AB, and you set up this homomorphism. H of 0 is A, H of 1 is AB, and H of 2 is BA. Okay. So now what is the inverse of ABA? So for that you have to consider strings over 0, 1, 2 such that H of that thing is ABA, right? And you can take help of this thing, that H of this A1 up to AN is H of A1 up to H of AN. So that means this is given here, right? So this is this for this example is ABA, right? So you have to figure out what is the breakup. Now this breakup can be either ABA or it can be A and then AB. So then I can identify this AB as H of 1, right? And this A as H of 0. So this whole thing becomes H of 1, 0. And similarly, I can identify this as H 0 and this BA as H of 2, right? So then this the whole thing becomes H of 0, 2. So you see that for both this thing, so H of 1, 0 is H of 0, 2, which is this ABA. And there are no other possible breakup. So if you take the inverse of this thing, you get back these two things. On the other hand, if you have say AB, so you cannot match this BA with H of 2, because you see then you have to match this A with something and B with something. Okay, this A can be matched with maybe H of 0, but you cannot match this B with anything. So a single B is not H of anything, right? So this breakup will not do. So the only breakup you can have is AB and AB, such that you can express this as H of something, and that something is here you have H of 1, and here you have H of 1. So this whole thing is just H of 1, 1, and it's H of nothing else. So you get this thing. On the other hand, if you have AABB, okay, so you cannot do anything. So this A either you can match with so you have to match this thing, since there is no AA, you have to match this thing with H0. Then you have you can have a H0, or you can take this thing. But whatever you do, you cannot so if you just take this to be H0, you cannot match BB. If you take this to be H of 1, then you cannot match B. So you cannot break this up into this say h of something, some symbol, h of some symbol, h of some symbol. You cannot break this up. So this is this is a string in delta star which is not image of anything here, right? So that is why the inverse image is just empty. Okay. So similarly here, instead of a single string, so here we are talking of a single string, you can consider a language here. So instead of just a single string, you can consider some language here, and you can consider the inverse image here. So that will be a bunch of string. Okay. And what is the inverse image? So it's a set of all x's here which map to this L. So again, just to be very clear, here we have sigma star, here we have delta star, and you are talking about a mapping. So something maps, so some set here maps to this thing, and this you are saying as L, right? So now what is this thing? So this is just H inverse of L, which is defined like this. So all the x's in sigma star such that H of x is L, right? So this is the standard definition. Now we will prove that regular languages are closed under inverse homomorphism also. And to do that, you see, what do we need to have in this H inverse of L? We should have all those x's such that this H of x is in L, right? And we are saying that if this L is regular language, then we prove that H inverse of L is regular language. So the first thing to do is to take some DFA for this regular language L, right? That's what we are doing. So you take some DFA M which accepts this language, say L, right? So now you consider some accepting path in this M, right, which accepts L. So this we are talking about L, because we are talking about M, right? Now you want to accept this A1 up to AN as a member of this H inverse L by some machine, where in this L this H of A1, H of A2 up to this thing is accepted, right? So yeah, so what is your x here? So this x is x is A1 up to AN, and here you see that, so this string, this H of A1 up to this H of AN, so this is just H of x, right? And you want that if Hx is in L, then this x should be accepted by some machine. So then you ensure that that machine corresponds to this language H inverse of L, right? And this tells you how to construct a machine for this. So if you have a path, say from Q to P in M, whatever M is accepting L. So if you have a path which processes this string HA, okay, so then you just put a direct edge labeled by A between this in your M prime. So you take, so we are constructing this M prime where we take the same states. So sigma is so you see here this M, it's accepting this HL, right? And HL is a language over delta, right? So that that means this HA, if you are talking about, this is a string over delta, right? So HA, so this is a string over delta, it's member of delta star. So if you have something like this in your M, you put a direct edge in M prime labeled by A. So what is this A? A is a symbol in sigma, right? So this machine that you are constructing, the input alphabet is sigma, right? Because it's the edges are labeled by symbols in sigma. So this M prime is a machine with input alphabet sigma. The start state is same, the final state is same, right? So and now we are defining this transition function, this delta prime. How? So we are putting this direct edge, so that means we have this delta prime QA say as P, which is the same P that we get from Q by processing HA in M prime. Okay, so it's the same P. So this equality, so they all are pointing to the same P, right? So what is this? So this is multiple transition, right? So that is why we have a hat. Hat is for multiple transition. We have this Q and we are processing this thing. So so this delta we know, right? We have a machine for L and there we know what delta is, and from this delta we are constructing this delta prime using this equation, right? And this is now the proof is pretty straightforward. So we need to prove that that h of x is in so we need to prove that h of x is in L, which is L of M, if and only if this x is in L of M prime. So this is, if we can prove this, it means that this L of M prime is actually H inverse of L, right? And we will prove a stronger statement, like for any state Q, if you take a string here x, and if you consider this delta hat, so transition for multiple, so transition using multiple steps, so this will be equal to delta hat of Q hx here. And how does that how does this help us to prove this statement? Because we can just take this Q to be Q0. So here is the proof. So if we can prove this, and now if we take this Q to be Q0, right? So then we have the same F, right? We have the same F for M prime and M. So this means that this hx is in so sorry. So this means that hx is in L of M if and only if this x is in the language of L prime, right? So this was the condition for acceptance in DFA. And the way we are constructing this machine, if we start with a DFA, we also get a DFA, right? Because why? because our M is a DFA. So for each Q and for a particular string HA, we get a unique path, right? So it's not that we can have multiple path going to some P, P prime, P double prime. No, this is a DFA. So we get a specific path, unique path. So for here also we get a specific arrow, right? It's not that we can put some other arrow labeled with A, some other arrow labeled with A. No, for A we get a particular this thing. So yeah. Now, how do we prove this? The proof is again just one line. It's induction on the length of x. Best case is this length is 0, so that means x is epsilon. And then by the definition of this homomorphism, in fact, by this substitution, we saw that this should be epsilon. And then for any q, I mean, if you take say epsilon here, or this is epsilon, right? This itself is epsilon. So then by definition of this hat, this extended transition function, this will be just q, right? So base case is done. And then for induction, you break it down into some smaller string and some symbol. And then by induction hypothesis, this holds for this smaller string y. So we have this for any q. Okay. And then what is this thing? So this you break down into first you process y and then you process this a. But this by induction hypothesis is this thing. So instead of this we have this. And then if we have this, now we use our definition for this. So by construction we have this, right? This is how we construct it. This is how we construct this thing. So this is how we construct it. So if that is the case, so what is this thing? So this will be hat of this thing, and this is the same thing, but here we have HA and hat. But then what does this means? So this first processes HY and then it processes HA from this state. So that means it processes HY and concatenated with HA. But then by definition of homomorphism, this is nothing but this, right? So yeah, we have proved this for this x. And this is just the proof. So yeah, this is substitution homomorphism and inverse homomorphism.